All right. Well, now let's go on and talk about some of the basic properties of superconductors. So the most basic property, I think, is that superconductors can conduct electricity with zero resistance. Here, let's take a look at this. Of course, what this means is that for temperatures below some transition temperature, the resistance of our superconductor is zero. And then above that, the transition temperature becomes finite. But you might wonder, how can we determine that? I mean, how do we know that the resistance is really zero and not just very, very small? Because any device that we use to measure resistance, or we pass a current through and then measure a voltage, has to have some lower limit of sensitivity. Well, the best evidence for zero resistance comes from what are called persistent currents. Let's see if we can illustrate this. Imagine the following. Imagine we make a ring of superconducting material. Okay? And now we're going to heat it up to a temperature above the transition temperature, so it's normal. And we'll place it into a magnetic field. Okay. My drawing's not so wonderful, but you get the idea. Of course, nothing particularly interesting happens. The magnetic field lines will thread through the ring so that there's some magnetic flux that passes through the ring. But so what? Now, suppose that we cool the ring so that the temperature drops below the transition temperature. Here's our ring once again. And then we're going to do something interesting. Then we're going to remove the external field. And what do you think will happen? Well, of course, what will happen is that the magnetic flux that threads through the ring will be trapped there. It won't go away even when we remove the external field. How do we know this is true? Because we know that we know that if the magnetic flux changed, then we would have to induce electromotive force around the ring. This would be a voltage. It would be the integral of the electric field as a function of displacement around the ring, right? That's Faraday's law. But we can't have an EMF, an induced voltage, inside of a superconductor, because a superconductor is a perfect conductor. A voltage would induce an infinite current. Okay? So instead, as the external field is reduced, we'll induce a current, a supercurrent, that will be just large enough to maintain the magnetic flux that threads through the ring. And now we can ask, how long will that current persist? You know, the same thing happens in any conducting ring. If we change the magnetic field through it suddenly, we'll induce a current that flows around the ring and tries to maintain the magnetic field. But in ordinary metals, the current will die away quickly due to resistive losses, and so the flux won't be trapped for very long. But in a superconductor, the current never dies away, and you can measure the magnetic field due to the trapped flux, and monitor it over time. And what you find is that it never decreases with time. Okay? So that's a good indication that the resistance inside of the material is really zero. There's even an application of this. Hold on one second. Here's an example of an application of these persistent currents. They're used in superconducting electromagnets, like this one. This is the same type of superconducting magnet that's used in the chemistry department upstairs. Only I didn't have time to get a picture of theirs, so I just found a picture of the same model online. Magnets like these always incorporate what's called a persistent switch. In a persistent switch, we do the following. So when we want to energize the magnet, so the magnet has a superconducting coil. When we want to energize the magnet, we open a switch, okay, and connect them so that the magnet is connected to a power supply, but current has to run through the power supply to go through the windings. And then we turn on the power supply like usual to induce a current in the superconducting magnet. We bring it up to the field that we want. But once we reach the field that we want, we do the following. We close the superconducting switch. Now we have a superconducting loop that runs through the magnet and then up to here and then through the switch, now closed. Well, since this is a superconducting path, all the current will go through the superconducting switch, which now has a resistance of zero, and none will go through the power supply. So now we can turn off the power supply, even take it away, and current will continue to run through the magnet forever until we either change something by opening the switch, or until the magnet runs out of liquid helium and warms up, or something else. So the magnet in the chemistry department sits at a constant magnetic field essentially forever, as long as it's taken care of and topped off. And so it doesn't need to be maintained by a power supply. That's a persistent switch, which allows us to make use of persistent currents in a superconducting electromagnet. One of the great advantages of these is that in their normal operation, they don't require any electrical power to operate the magnet. All right. The next phenomena I'd like to talk about is called the Meissner effect, and it's the ability of superconductors to expel magnetic fields when they're cooled below their transition temperature. And well, it's best just to try to explain this before I try to talk about it much. So here, let's go to the notebook. All right, here's the idea. Suppose I have a chunk of superconducting material here. Here it is. But to begin with, let's suppose that it's heated above the transition temperature, so it's in the normal state. It's just a normal metal. And now suppose we place it in a weak magnetic field. So the magnetic field will penetrate through the material, as you might expect for any normal conductor, okay? Now, suppose we cool to a temperature below the transition temperature. What happens in the Meissner effect is that the magnetic flux is expelled from the material. So that the magnetic field inside the material goes to zero. Kind of mysterious, right? What's going on is that when the material is cool below the transition temperature, superconducting currents are induced around the outside of the material. And these create a magnetic field which exactly cancels the field inside the superconductor. That's the Meissner effect. Now, interestingly, the Meissner effect is not just a consequence of perfect conductivity. It's not like the persistent currents that we talked about a minute ago. Instead, it's something else. And we can illustrate that. Here, let's imagine what would happen in a perfect conductor. So just to make my point here. Oh my gosh, I'm spelling it wrong. What I want to say is that the Meissner effect is not just perfect conductivity. Because perfect conductivity makes a different prediction. For a perfect conductor, meaning a conductor with no resistance, as we mentioned a moment ago, inside of a perfect conductor, there can be no electric fields. Because otherwise we'd induce infinite currents. And that means that the integral of the electric field around any closed loop must be zero as well, since the electric field is zero everywhere. But this is just the electromotive force around the ring. And we know that this is equal to the rate of minus the rate of change of the magnetic flux through the circuit, through the loop. And the magnetic flux can be written as just the integral of the rate of change of the magnetic field integrated over the loop. Okay? So if this is always equal to zero, which is what we expect for a perfect conductor, then what that really tells us is the rate of change of the magnetic field must be zero inside the superconductor. Okay? But that would just mean that the magnetic field had to be constant. So in a perfect conductor, we'd expect that the magnetic field would have to be constant inside. But the Meissner effect is something more. It says that the magnetic field is not just a constant, but that it's zero. Okay? So I wanted to mention this. This is a important and kind of mysterious effect, but the Meissner effect is not just a consequence of perfect conductivity. In fact, it's almost the other way around. So that's the second property of superconductors that I wanted to introduce. I have a few more, but I think I'll wait till the next video to talk about them.